In this video, we're going to talk about how to interpret the slope and the intercept for models that include an interaction term. But before we do that, I want to talk about a couple of changes that we want to make to the parameter estimates table. So first of all, the parameter estimates table, the default is to use effect coding. So we've talked about that before. I'm not going to go into the details of effect coding for interaction just because I think indicator coding is easier, and I don't think there's really any reason to talk about both. But of course, if you're curious, let me know and I can tell you more about effect coding. The other problem is that the default here is to center the variable. So they're taking the quantitative variable and subtracting off the mean. This is very similar to what we did when we standardized our explanatory variable, except that they're not dividing by the standard deviation. If you just subtract the mean, that's called centering. And there's some reasons to do that. We may talk about that a little more later on, but it definitely makes things harder to interpret. And so for simplicity's sake, I'm going to show you how to get rid of that and just use the regular quantitative variable. Okay, so we're going to start off with analyze fit model, just like what we had before. So remember, fit model is what you use anytime you have more than one explanatory variable. We've got price as our response, and we want to include both the size and the location in our model. But now we're also going to use an interaction term. So I'm going to highlight size and lake, and I'm going to click cross and do it that way. By the way, I did that just by holding the control key so that I could highlight them both at the same time. Okay, so now I've got my two variables and the interaction term. I also could have done that with the full factorial, kind of like I did for categorical data earlier. Okay, and then we're actually going to change something here before we even click run. So we've never had to do this before, but I'm going to click the little red arrow next to model specification. And by default, it says center polynomials. We're going to uncheck that because we want just our plain quantitative explanatory variable. And then I'm going to click run. So I can tell that this did what it was supposed to because now when I look at the size, it just has regular square feet. It's not doing square feet minus the mean. But this still is using the effect coding, and I want to use indicator coding. So this is the same as what we did for additive models. I'm going to go up here to response, estimates, and change it to indicator parameterization estimates. So then all the interpretations that I'm going to do are coming from this table. So just make sure that you know how to get those estimates because I'm only going to go through the details of how to interpret these. And if you were using different numbers, of course, those would have different interpretations. So we want to make sure that we're working from the same table. And all the instructions that I just went through are here in these bullet points. So we want to start by noting how our indicator variable is defined. So we need to figure out which group is the baseline group. The baseline group is just whichever one is not mentioned in the output. So like here it says lakefront in the output. So x2 equals 0, the baseline group is for not lakefront. And then 1 is for lakefront. So we can see that our model looks a little bit different than an additive model. An additive model would have the two terms with x1 and x2, but now we have this new interaction term. So it's literally just x1 multiplied by x2, and in fact you could create your own column, you could multiply the two together and then just feed it into the model that way. And that's exactly what JMP is doing behind the scenes when we do the cross term, when we do the square feet cross lake. So let's start off just by writing out our equation. So our predicted value of y, our predicted price, is going to be for the intercept $58,113. I think I'm just going to keep rounding to whole numbers just to make our calculations a little bit easier. Plus 84 times the size of the house, that's our x1. Plus 28,651 times the location, that's our x2. And then here's the new part, the interaction term, plus 136 x1 times x2. So we've got the product of our explanatory variables there with our interaction term, and that has its own slope. So let's start with the houses that are not on the lakefront, since the baseline group is the easiest. So for the baseline group, remember that's where our second explanatory variable x2 is just equal to 0, right? That's how we've defined our variable. So if we were to plug in 0 for x2, both of those terms that have x2 in them would just go away. So we'd be left with just our original regression equation. We've got 58,113 plus 84 times x1. So this would be the prediction equation for the houses that are not on the lakefront. In other words, that's the prediction equation for that blue line in the graph. For houses that are on the lakefront, we're going to need to make some adjustments. So this is where we're plugging in x2 equals 1. So it starts off the same. We've got the same intercept and slope, but now we've got some adjustments. So I'm plugging in 1 for this x2. So I'm just going to end up with that constant, right, plus 28,651. And then I'm also plugging in 1 here, but in this case, obviously I still have the x1 as part of it, so it ends up being 136 times x1. So now I have two constants, and then I have two terms that have x1 in them. So let's go ahead and show that step just to kind of think about combining these terms. So I'm combining the original intercept, the intercept for the baseline group, and I'm adjusting it using the coefficient for location. So that number, I can think of that as like an adjustment for the intercept. And then I'm going to do the same thing here. I've got the original slope, the one for the baseline group, and then I'm adjusting it for the lakefront houses, right? So since we have an interaction term, not only are we adjusting the intercept, shifting the lines up and down, but we're actually allowing the slope to change. So when we put that together, the new intercept for the lakefront houses is going to be 86,764, and the new slope is going to be 220. So this is the slope relating size to price for the lakefront houses. So again, just to emphasize what it means to have an interaction means that you have different slopes, right? That whether the house is on the lakefront or not is going to change the price per square foot. So for houses that are not on the lakefront, this means that as the size increases by 1 unit, as size increases by 1 square foot, then the price is predicted to increase by this amount. So price is predicted to increase by $84. Whereas if the house is on the lakefront, we have a much larger slope. So here, as the size increases by 1, this part stays the same. The size increases by 1 square foot. Now price is predicted to increase by $220. So it makes a big difference. Price is predicted to increase by $220. So notice that this is different than an additive model, right? In an additive model, we said they have the same slope interpretation, just holding the location constant. That's the way we describe it when we have two lines with the same slope. Here, the lines have different slopes, so we have to interpret those slopes separately.